Bubble sort is one of the simplest sorting algorithm, and in this video we will be looking at the core idea. We will be looking at an example that brings the core idea into action. We will write the code and understand the code, and we will also be looking at the performance of the code that we have written with the help of time and space complexity. And finally, we will be looking at the key terms and features of bubble sort that are very important with respect to interviews. So the core idea of bubble sort is very simple. It is super straightforward and intuitive. So the idea is we will be looking at unsorted pair of adjacent elements. So we'll be looking at unsorted pair of adjacent elements, and we will be comparing them. And if we see that the particular pair is out of order, we will swap them so that the order is restored. Now let me give you an example. Let's say that you have an array 5, 1, 4, and 2, right? So how many adjacent pairs do we have over here? So you can form the adjacent pair by the first two elements. You can form the adjacent pair by using the next two elements. And finally, you can form the third pair by using the last two elements. So in general, if you have an array of n elements, you can form n minus 1 adjacent pair of elements. All right. So for each of these n minus 1 pairs, what we will do is we will compare them and see if they are in right order. For example, one of the pair is 5, 1. So here we compare the first element and the second element. So if the first element is not smaller than the second element, that means that we are out of order. And in that case, we simply swap them. So we simply swap them using any simple logic. You could use something like swap a comma b, where a would be one element and b would be another element. Or you could use your regular temporary variable, where you store one variable. Let's say temporary equals a, and then you say a equals b, and then b equals temp. So you could do something like that as well. The idea still remains that if we find any pair that is in violation of the order, we will swap it and we will ensure that the order is retained. So we do this at every stage of the algorithm. We find the unsorted pairs, we will compare them, and we will restore the order if it is required. And what you will see is that in the next example that I'll be showing you, the visualization, in that we will observe that at every stage, the largest element will make its way towards the right hand side of the array. So it will make its way to the intended location, right? So the name comes from this fact that the largest element seems to bubble away towards the right to its correct location. So that is how the algorithm got the name of bubble sort. So now let's head into the visualization and I'll explain you at every step what happens. All right, so let us consider this array. So this array is clearly unsorted, and we will try to see how bubble sort will sort it step by step. We will also track the number of passes that are completed, and we will also track the current pass. So when we begin, we consider that all the elements are unsorted, right? So we have 5 unsorted elements, and we have seen that with 5 elements, we can form 5 minus 1, that is 4 adjacent pair of elements. We begin by comparing all the 4 adjacent pair of elements one by one, and we will swap them if they are in the wrong order. In the first step, the first comparison, we compare the first 2 elements. Now they are clearly out of order. We will swap them, and we will continue with the second pair of element. So the second pair also happens to be out of order. So we will swap them as well. The third pair also is out of order. So we will swap them. And finally, we'll come back to the last pair, and that fortunately is in the right order, so we will not swap them. So by that, we completed one pass and we found out that the largest element is now at its correct location. So we now move on with our second pass. In the second pass, we look at how many unsorted elements do we have. We have 4 unsorted elements. So 4 would form 4 minus 1, 3 pair of elements, and we will start comparing all the 3 pairs. 1, 4 is the first one that we compare. That is in the right order. 1 is smaller than 4. We will now move to the next pair, 4 and 2. That is not in the right order, so we will swap them. And the third and last pair is in the right order. So we now complete 2 passes, and we have the largest as well as the second largest element in their right location. So moving on to the third pass, where we have 3 elements, we will have 2 comparisons to do because we will have 2 pairs. So let's compare the first pair. It's in the right order. Good. Nothing to do. The next pair is also in the right order, so we don't have to do anything. So with that, we complete 3 passes and we find out that the largest, the second largest, as well as the third largest element all are now in their right location. Now we are left with only one pair of element, right? And we see that that pair is also in the right order. So with that, we completed 4 passes. And now right now we're only left with one more element. And this element has no other place to be. So if an array of n elements, out of which n minus 1 are sorted, the last element has to be at its sorted location automatically because there isn't any place else for it to be, right? So with that, we can conclude that the whole array is sorted if n minus 1 elements are already sorted. So to sort an array of n elements, we only need n minus 1 passes. And here we can see that we had 5 elements and we only required 4 passes to completely sort it. So I hope by this example, you understood how the largest element at each stage bubbles its way to its right side and it always ends up being at its right location. So after looking at the example, I hope the idea is very clear. Let's now condense the core idea into 2 simple steps. The first step is you compare adjacent pair of unsorted elements, and if they are out of order, we will swap them so that we restore the order. And if they are already in the right order, then we don't do anything, we simply continue the loop. So that was step 1. The step 2 is that we repeat step 1 for n minus 1 iterations. So I also explained you why n minus 1 iterations. That is because if you have an array of say n elements, and if the n minus 1 elements are in the right order, the last element is automatically present at its correct location, and hence we don't need to run the algorithm one more time. So in the example, we had seen that we had 5 elements, and with 4 iterations, we were able to completely sort the array. Before writing the code, let's also understand how many comparisons do we do at each step. So initially we had n elements, all of them are unsorted. So we had n minus 1 pairs. So the number of pairs is equal to the number of comparisons. So we had n minus 1 pairs, so we do n minus 1 comparisons. After the first iteration, we observe that one element goes to its correct location. So we are left with n minus 1 unsorted elements. So n minus 1 unsorted elements would mean that we have n minus 2 pairs of unsorted elements, right? So in this manner, we will reach a stage where we only have one pair, right? So we have 2 unsorted elements and those 2 account for one pair. So you can see that the total number of comparisons that we do, it forms an arithmetic series, n minus 1 plus n minus 2, so on until we reach 1. So this type of arithmetic series, where each term differs by a factor of 1, will always sum to n into n minus 1 over 2. So if an array has n elements, the total number of comparison that bubble sort does is n into n minus 1 over 2. I hope this is clear. This will be very useful when we compute the time complexity as well as when we write the code. I hope that the core idea is very clear at this point. Let's now write the code. So here I have a simple program. All it does is it displays the existing array, the initial unsorted array, and then we apply bubble sort, and finally we display the sorted array. So the thing that concerns us over here is writing the bubble sort function. So it reads the array using reference, so we don't return anything, and we do the sorting in place, right? So let's do it right now. So the first thing is n. Let's get the size of the array. So we saw that we need to do n minus 1 iterations to sort the array. So let's write a loop that runs for n minus 1 times. And for each iteration, we have to compare all the adjacent unsorted pairs, right? So for that, let's do another loop. So how many times we need to run the inner loop is based on the number of pairs at each stage. So when we are at I equals 0, we are at the first iteration. So the first iteration means that we have n unsorted elements, so we have n minus 1 pairs. So the inner loop must run for n minus 1 times for the first iteration. But for the second iteration, we only have n minus 1 unsorted elements because one element gets to its sorted location, right? So n minus 1 unsorted elements means that we have n minus 2 pairs. And for n minus 2 pairs, this inner comparison loop must run for n minus 2 times. So what can I add over here so that the loop runs based on the iteration number? So I0 means n minus 1, I1 is n minus 2, right? So all I could do right now is n minus 1 minus I. So this will make sure that based on which iteration we are doing, the number of comparisons will also be based on that. So when I is 0, we do n minus 1 iterations. When I is 1, we do n minus 2 iterations. And when I is 2, we do n minus 3 iterations, right? You get the point. So in this loop, we will just make a simple comparison where we compare array of j with array of j plus 1. So if j is larger than j plus 1, that is out of order, right? The element on the left hand side should be less. So if it is out of order, all we will do is swap array of j with array of j plus 1. That's it. It was a very simple algorithm. It's only about 4 or 5 lines of code. So this should give us the sorted array. So let's now quickly compile the file and run it. So we have no errors. The compilation is good. Let's now run the file. So we can see that the unsorted array is, clearly unsorted. And once we run the algorithm, we have the sorted array in place. So the code is very simple. Just focus on this particular step so that you don't get confused. Now let's move on to time and space complexity. So the first assumption that we make when we compute the time complexity is that every comparison takes a constant amount of time. So every comparison in this step would take a constant amount of time. Let's call that C. So if I had to write it down, the total time would be the total number of comparisons, which we have seen earlier is equal to n into n minus 1 over 2. And I could multiply the total number of comparisons with the time taken for each comparison. So if I expand this expression, that would be Cn square over 2 minus Cn over 2. So if I consider C dash a new constant to be C over 2, we could simplify this expression over here as C dash n square minus C dash n. So we know that for time complexity analysis, we only consider the leading terms and we ignore the non-dominating terms. So in this case, the leading term is n square. So we can say that the time complexity is of the order of O of n square. So the time complexity of bubble sort is quadratic. Let's now look at the space complexity. Bubble sort might not be good in terms of time complexity, but it is great when it comes to space complexity. That is because we don't use any additional data structures. So no additional data structures were used. That means that we only use constant amount of space. So that constant could be something like this or, some overheads that we maintain and that's it. We don't really use any additional data structure or any extra array. So we can say that the space complexity of bubble sort is O of 1. So before we end the video, let's take a look at some of the key features of bubble sort. Bubble sort is a stable sorting algorithm. It maintains the relative order of same elements. So if I say that I have an array that says 1, 2, 3, 4, and 3, if I sort it, this should be 2, 3, 3, 4, and 5, right? So let's call this 3, 1, and 3, 2. In the sorted array, it would be 3, 1, and 3, 2. So the relative order is still maintained, right? So the second point is it is an in-place sorting algorithm. It must be very clear by this point that we don't use any additional data structures and the array is sorted in place, right? So that makes it use no extra space and hence it is an in-place sorting algorithm. The third one is pretty clear from the name itself. It is a comparison based sorting algorithm, and that's because we compare adjacent elements at every stage. So, with that, we have arrived at the end of the bubble sort lecture. We looked at the core idea, we looked at in visualization, we wrote some code in C++, we looked at the time and space complexity analysis, and some key features as well. So that's it for this video. In the next videos, we will be looking at other sorting algorithms like selection sort, insertion sort, merge sort, and quick sort.